Hey everyone, welcome back. What I want to talk about today is the fifth section of our chapter 10. Look, it's up here, chapter 10.5, page 289. So we're going to do that. I might have to break it up into two bits. It's pretty long. This is one of the harder parts. This is where it starts to get really hard, and this will then carry on into your Unit 3 work later in the year, where you're talking about projectile motion and inclined planes and stuff like that. So this becomes really important. What we've done in the first four sections is really just going over a lot of the grade 10 work, introducing a few new terms like vectors and displacement, and giving you a few ideas. But what I want to do is have a look at more complicated things. This is where you've got uniform acceleration. Now, the two cases we're going to look at in our prac in week 6 will be just dropping a ball. So you'll be dropping a ball in the lab or off the balcony outside. I think you might have done it in grade 10, but we're going to do it in a lot more detail. So you drop it and you take the time for it to reach the ground and so on. And we start plotting graphs, doing uncertainty and so on. But that's acceleration due to gravity. Now that's about, it's 9.8 meters per second squared in the downward direction. But we're also going to have a look at other cases where we're going to slow it down. That's hard to measure because it's going so fast. So what I've got set up for the lab, a number of these aluminium, like they're little ramps. We've got smaller ones, and you'll be letting a ball roll down the ramp and measuring the time it takes to do a certain distance. So when it's not much of an angle, it rolls slowly, and that's easy to measure. But as you have a bigger angle, it gets faster and faster. So that'll be something we can do in next week, week 6. Okay, what I'd like to have a look at is just to quickly go over what acceleration means again. Now, you did this in grade 10 for your physics unit, but let's have a look. Now, we defined acceleration, and the CEL part, celere, that's a Latin word meaning speed. Now, you might have seen the equation E equals mc squared. Some of you did it when you did your Big Bang research assignment for grade 10. The C in E equals mc squared, which is the speed of light. C is the speed of light. Einstein just used the Latin word celere, C-L-E-R-E, to stand for speed of light, C. So that's what the celere part in acceleration means. So acceleration has the symbol A. Now it's a vector quantity because you can accelerate in a particular direction. So really I should have a little half-headed arrow on top of that. But I'm not going to worry so much about the vector nature of this at the moment, so I'll just leave that out. Now, you would have learnt that it's equal to the change in speed over the time taken. Now, that's the time elapsed. Now, just to make sure you realise that. So, now that was the final speed, now minus the initial speed over the time. Okay, now there's nothing tricky in this. This is all fairly straightforward. Now, for the final speed, we could use v for speed, or velocity, with a little subscript f. Now, you could do that, and you'd use v initial. Now, some textbooks do that, but what we're doing is what the syllabus does, and what I've done in the previous editions of my text. I've used the symbols. Final speed is v, initial speed is u. Now you would have learnt that in grade 10, so that's nothing tricky, over t. So A equals that. The simplest way to remember it is u comes before v in the alphabet, so initial comes before final. Now that'll be, when you do your end of unit exams, you'll have a formula book and that'll be in it. So you don't have to learn these things. That's a formula book formula, and you just look it up. I won't tell you what the symbols mean, but it'll give you the formula. Now look, let's just do a a simple example of this. I'll just get rid of this and I'll just keep it up here so we can see it. Now another way of writing that, of course, would be delta V on T. Either way you can do it. This is probably the more common way. Now often you learn it as V equals U plus AT. And you just cross multiply and rearrange things and get V equals U plus AT. In fact, I think in the formula book it might be written like that. It means the same thing. Okay, let's get rid of this because you won't need that for this part of the work. Now, let's imagine we're talking about something that's accelerating. Now, a good example might be say a big car like a Holden Commodore or a Falcon or something like that. Now, let's imagine it can go from 60 kilometres per hour. Look, I'll just call it kph. That's not an SI unit, it's just an abbreviation. Let's say it goes from 60 to 100 kilometres per hour in, takes about 8 seconds. Now that's flat out. If you were driving a Commodore or a Holden, big Holden, you think of yourself going along the road at 60, that's the maximum speed, suburban speed, and you accelerate to 100. And you think, how long would that take? If you tried to estimate it, you'd think, 1, 2, 3, 4, 5, 8 seems quite reasonable. Let's do an acceleration on that to see what the change in speed over time. Now I'll work in SI units, the international system, so I'll change this to meters per second. Now I won't bore you with it now, but 60 is about 18 meters per second, and this is about 28 meters per second. Okay, it's something pretty close to that. So A equals V, which is the final speed, 28 minus 18 over 8. So that's 10 over 8, which is 1.2. Now the units, we've got to be careful with these units, and students from grade 10, when they first meet the way we write it for grade 11, get a bit tangled up. Hopefully by now you're okay that the 10, the meters per second is in ms to the negative 1. That just meant meters per second. Okay, so ms to the negative 1. Now you're dividing this by seconds. So if you think about it, you're dividing that by seconds to the power of 1. And you know that if you take that up onto the top line from the denominator up into the numerator, that becomes ms to the negative 2, because that thing became s to the minus 1. You add them together and you get s to the minus 2. Oh, look, there's mozzies. So I'm just going to rub that out and put that down as ms to the negative 2. Now that's my unit for acceleration. Okay, ms to the negative 1 for velocity, ms to the negative 2 for acceleration. Okay, let me just try one more example to finish off. Another car, and I don't know if you could guess this, but another car is the Hyundai i30. I had a look at the data for that. It can go from 60 to 100 in about 4 seconds. Now you might think, this is a little car, it's a smaller engine. This has got an engine of about 4 litres or something like that, 3.5 litres for the capacity of the engine. This thing's around about 2 litres. So the engine itself is about half the size, but it can do it in a quicker time. Now I don't know if you can sort of work out what must be going on there, but it's to do with the mass of the cars. Now this will come up in the next chapter when we talk about Newton's laws. You know, the heavier the mass of something, the harder it is to accelerate. Even though this is heavier, it's got a bigger engine, but when you weigh the two together, the lighter mass of this thing means it accelerates faster. So that'll be 18 meters per second to 28 in about 4, and that's, what's that, about 2.5 seconds, 2 meters per second. Yeah, that's not exactly 1.2. That's meters a second to the -2. Okay, so the acceleration is about twice as much because it does it in half the time. Okay, so that's the meaning of acceleration. Now, look, I'll just mention something else while we're at this before we go on. If you think about it, you have velocity is distance on time. Acceleration is, well, this is actually change in distance, or change in displacement, I should say. This is change in velocity over time. Okay, so acceleration is that we have the symbols V, A. Now in maths you might call this the first differential. This would be the second differential, because when you think about it, it's in terms of calculus, you're doing the second differential on this thing. Oh, you're doing another differential, you're dividing by t. So you take that thing, or you start off with s divided by t, and then you take this thing, which is s divided by t again. I don't know if you've ever thought, what happens to this? Now that's the third differential. Is there a name for that? Rate of change of acceleration. And there actually is one. It's called the jerk. Now I know you think I'm joking here, but a jerk is a proper term. It's a rate of change of acceleration. Now, for instance, some good examples might be if you're looking in train lines. One good example is if a train's going around a curve, because it's changing its direction, it's accelerating. Remember, acceleration is a change in velocity. Well, velocity is a vector. So even if it keeps going at the same speed and it turns, that's still acceleration. Now, if you have that turn nice and smooth, you don't get a change in acceleration. It accelerates around nicely. But if you don't have that curve right and it's a bit bent, actually the acceleration changes as you go around, and that's called jerk. Now they try and minimize the amount of jerk in any sort of mechanical device, really. Roads, trampolines, space shuttles, all this sort of stuff. They try and minimize the jerk. Now I know you'll think this is nuts, but you can look it up if you ever wanted to. You can do the next differential of jerk, so it's change in jerk divided by time, and that's actually got a symbol S. It's like this symbol here, so people often get confused, but this is called snap. Okay, it's the rate of change of jerk, and as you might have guessed, there's a change of snap over time. This thing here is called crackle. I know you think I'm joking, but it's true. You go and look it up in Wikipedia, and you can probably guess what this is. The rate of change of crackle is called, you guessed it, pop. Okay, so jerk, snap, or crackle, pop. You can buy t-shirts with that on it if you like. So velocity, acceleration, jerk, snap, crackle, and pop. Now these things aren't important for senior physics. We don't deal with them. But if you're doing an engineering degree particularly, you might in second or third year start investigating the rate of change of snap, for instance, or jerk. In the space shuttle they used to worry about these things all the time. I know in trampoline physics looks into the snap and crackle and so on. I'll explain a little bit more about that later without actually, you'll never be asked those words in senior physics, but just interesting to know. Okay, let's move on and have a look at a real life example. Now, I could do this one. Let's imagine you're, like I said before, you're rolling a ball down an incline. Now you'll be doing that as a prac in week 6, in the double probably. Depends on how we go with dropping the ball. But let's imagine you're collecting data on this. Now that'll be in seconds, meters, and meters per second. Okay, now I won't do it for very long. We'll just say we're collecting data for 4 seconds. They all start off at 0. Now let's imagine after 1 second the ball is going at 4 meters per second. Okay, let's say you had some way of measuring it. Now we've got programs that you can get on your computer. The school owns them. It's called Logger Pro. I will show you it later. But if you can actually work out the speed at a particular time. You video it and you can work it out. So let's say it goes 4, 8, 12, 16. So that's the speed every second. And you can see this. Okay. Now, the question is, how far did it go? If you plotted that versus that, you don't have a big problem. Look, I'll do it here so it's pretty easy to see. 1, 2, 3, 4. That's time. 2, 4, 6, 8. And that's V. Okay, if you plot that, 0, 0, I'll do it in another colour. 0, 0, 1, 4. Whoops, I needed 16. 2, 4, 6, 8. No, I'll just do that again. I forgot I was doing velocity. I'll just get rid of that. Let's do it as 4, 8, 12. Now that should do you. That'll work. That's V. So 1, 0, it's 0, 0, 1, 4, 2, 8, 3, 12, 4, 16, and you can draw a straight line through that. Okay. So that's the first graph. Now the second graph is I'm going to do a T versus S one, but we don't have S data. Now you might, when you collect the data for the ball rolling down the incline. We can work it out though from something I told you the other day. If you look at the average speed for the first second, now there's the first second of its travel, the average speed starts off at 0, after 1 second it's doing 4, so the average is 2. Okay, so what the ball has done is it's travelled for 1 second at an average speed of 2 meters per second. So the distance travelled is 2 meters. Think about this, between the 4 and the 8, the average is 6. So the ball has travelled for 1 second at 6 meters per second on average. So it's gone 6. Here, average of that is 10. And for another 1 second, so it's gone, oh, wait a second. This is how far it's going. It's plus 6, plus 10, plus 2. That's how far it's travelling. And then here it's 14. The average of that's 14, so it's doing another 14. So it started off at 0. After 1 second, it's gone 2. So these are my values. It's going at 2, and then it's going at 8, because it had gone 2, and then it does another 6, so it's going at 8, 18, and 32. So the displacement of the ball in meters is that. Now that's 32 meters, that's huge, but you could imagine these could be 0.2, 0.8, 1.8, 3.2 meters, even that's long. You'll be dealing with a thing, a aluminium trough or aluminium ramp about a metre, 1.2 meters long, and that should work out right. Now look, I'll just rub these out because that's not important. So what I'd like to do is to plot these two values here. Now it's going to be a bit tricky. I need the room. Now if I was at school in our lab, I'd have the big board to spread out on, so I'm a bit stuck here. But let me just check this thing to make sure we understand what's going on. If you worked out the gradient, now this is of a VT graph. So VT graph, the gradient equals, I'll just get rid of that. The gradient of a VT graph is 16 on 4. And the question is, what does that 4 represent? Well, it's meters per second. Now you know the gradient is change in y divided by change in x. So this is meters per second divided by seconds. So that's meters per second, which is acceleration. If you look at this, the acceleration is 4. Every second it's changing its speed by 4. Okay, so that's what acceleration means. So that's 4. So this is acceleration. So keep that in mind when I make a summary later. The gradient of a VT graph is acceleration. What about the area under? Now the area under a VT graph, remember I was getting tricked up on that before. The area under is just base by height on 2. So it's 4 times 16 on 2. So that's 32. Now when you think about it, this is meters per second times seconds, and they cancel out, and that just becomes meters. Okay, so the area under a VT graph is displacement, the final displacement here. Okay, so the gradient is the acceleration, that's the change in velocity per second, and the area under it for the full 4 seconds is the final displacement. So keep that in mind when we make a summary. Now look, I'm going to rub most of this out so I can plot these two things, and so just forget about that for a minute. If you're stuck, you can go back and look at the video. Now look, I need a bit more room here. I'll just write this over here. So that's S in meters. Okay, I can rub all this off. Right, now this is going to be a bit tricky. I'm going to plot 0, 1, 2, 3, 4. Now, if I was using Excel, I could get a really nice graph. Or if I was doing it on graph paper, now I tried it on graph paper before, but I needed to do it big enough for you to see, and it's really awkward. But I'll just do it this way. And we want to get up to 32 meters. So let's go up in, we can go up in 4s. 4, 8, 12, 16, 20, 24, 28, 32. This should work. Okay, so let's see how we go. I'll just do it in another colour. Now this is time in seconds, and this is displacement in meters. Okay, 0, 0, 1 it's at 2, 2 seconds it's at 8, that's about there, 3 seconds it's at 18, which is around about there, and 4 seconds at 32. So that's, I can't really get there, but somewhere like that. Now if you look at that, you join all that together, we get this. Whoa, that's not very, you get the idea. It should be a little bit more curved like that. Okay, I'll put that back on there. Okay, now if you had to say what shape that is, remember we had a choice of things like y is proportional to x, x squared, x cubed, 1 on x squared, square root of x, and all those sorts of things. I think you'd be pretty happy to say this is y is proportional to x squared. That's what it looks like. So this to me, and to you hopefully, looks like a y, which is s is proportional to t squared. Okay, so that's what it looks like it's forming. Now, the question is, what can we get out of this? Now, you might remember I said in an earlier section that to do instantaneous velocity, it was a bit tricky. I wanted to leave it until I was actually looking at something that was changing. Now, I don't know how this is going to work. We'll see how it goes. I might have to tell a few lies in here to make it work. But let's imagine we were doing this to get the slope at a particular point. So you can't have a single gradient for this, because when you think about it, the gradient is 0 there. It's about that, and then it gets steeper. So the gradient is it's the gradient to the tangent of the line. So what I'd like to do is to draw a tangent in. Just have a look at one example. Now, I don't know how this is going to work. I want to draw a tangent in, say, there. So that's at that point there. Now that's not a very good one. 16, 18, at 3. That point really should have been a green one. If I drew that properly, it would have been here. You might remember when I tried to draw it before, it was something like that. So it goes, whoops, it goes more like that. Okay, now what you're looking for when you draw a tangent is to make sure, and I haven't got it done very well here, but you want to have it so that it's only touching at the point you're talking about, the 2-second mark. Now, the amount of space there should be around about the same as the amount of space there. So you've got it so that it's evenly positioned around that point. Let's have a look at the gradient at that point. So that point there was 18, if you remember. 18 at 3 seconds. And this point here, now that's at 0. And if I drew that properly, I tried it earlier and it came to, I think this came to a little bit more than 3. I think according to the line actually came something like this. Okay, when you draw it, that was 1. So that's okay for 1. This was around about 3.25. Okay, so I'm going to work out the gradient. Now you know that's 18 there, and see what we get. Now you might think I'm sort of making this up and adjusting things to work out, but if you do it on graph paper, which I did, it works out neatly. So let's have a look at the gradient at 3 seconds. Now the gradient is change in y, which is 18 to 0. So it's 18 minus 0 over change in x. So it's 3.25 to 1, which is 2.25. Now, if you work that out, the gradient comes to, I think it comes to 8. 8 twos are 16. Yeah, that comes to 8. Now, the question is, what was 8? What had a value of 8 at, sorry, this is 2 seconds, not 3. This is 2 seconds here, because that's where I made that point. So the gradient at the 2-second mark, which is that line there, has a value of 8. Now the gradient is just S on T. Now, if you think about what S on T is, that's velocity. So this is meters divided by seconds. So the question is, what was 8 meters per second at 2 seconds? And if you look back to the original thing I had here, for V, I had 0, 4, 8, 12, 16, that's meters per second. Okay, so at 2 seconds, it's probably unfortunate that I've chosen numbers that give a displacement of 8 as well, but the what we can say is that the instant, or the gradient to a point on an ST graph is the instantaneous velocity at that point, because there it is there. So at the 2 second mark, it was going at 8 meters per second. Okay, now nothing else we have to worry about for an ST graph. Like before, the area under doesn't mean anything, it's only the gradient. Okay, now I'm going to sum that up in just to write it down so you've got it all neatly. Just those points about the graphs. So I'll just get rid of all of this. And see if this makes sense. So we have an ST graph that looks like that, a VT graph which would be constant. Okay, no, wait a minute, I'll have to check that again. It was constant. No, the velocity was increasing. What am I saying? The velocity was going up in 4s. So it was going, after each second, it was increasing by 4. Sorry, you got that. Okay, so this was this y is proportional to x squared. This is y is proportional to x. Now the acceleration, which was, this is v, the acceleration, if you think about it, I told you it was increasing by 4 every second. So the acceleration was constant. So it started off 4 meters per second was the increase for the first seconds, and then the next second increased by another 4. So the acceleration was like this. Okay, it sat as a straight line. Now, that's what you have to remember for this stuff. So we can look here at the gradient and the area. The gradient of this thing, the instantaneous gradient, is v, but that's only the instantaneous one. Remember, I'm not going to, I could probably write this in here, instantaneous, EOUS. I'll put area down a bit lower. And the area was nothing, didn't mean anything. For this thing here, the gradient was the acceleration, and here the gradient was 0, because it's not changing. The acceleration was uniform, it's staying constant. The area under, I told you there's nothing there. The area under this is the displacement. The area under this, well, you could work out it means something, but I won't. If you think about it, it was 4 times 4 is 16. You know, the question is, what does an area of 16 mean? And I think that was the final velocity. So you could write final velocity, but it's something we never do. Okay, now to finish this off, I just want to, I probably should put both types of graphs up so you've got them. So this was the graph for 10.5 for that section there. I'll just get rid of this and sum up for you. So this is what we did so far. For 10.4 or 10.4, we did ST, VT was constant, and AT was 0. I better do that in a different colour so you can see it. AT was right along this bottom line at 0. Okay. Now, the acceleration there was no acceleration. It kept a constant velocity. So this was 10.4 and 10.5, which is uniform acceleration. This was no acceleration. This was uniform acceleration. And this is what I just drew on the board. ST was like that. VT was like that. And AT was some number there. Okay, so you can see the relationship between the three. Now you'd be expected in questions, you know, I'll give you some data or some object. A good one is dropping a golf ball into a swimming pool. You know, how does the ST, AT, VT and all the rest of it vary, and so on. So the experiment you're going to do with either the ball rolling down the ramp, which has low acceleration, might be only 2 or something like that, compared to dropping a ball off the veranda, which will be 9.8. This is the one you're going to look at, and that's the one the syllabus concentrates on. Okay, now I'm going to stop there because I want to break up 10.5 into 2 parts. Give you a breather. That's probably 20 minutes or so. I'll give you a breather, and then I'll do 10.5 part B, where I'm going to look at a couple of worked examples. There's only 2, but The second one is a real killer, and it's difficult. So I want to make sure you're fresh and ready to go. So I'll stop there, and that's that. So thank you.